Okay, so let's go through the review. We'll see how far we get. We don't want to get too far because we want you to take it in chunks and not feel overwhelmed. But what's that? There's one person on, and then if anyone else wants to watch it. So yeah, so this will be recorded too. So if you want, if you're going through a problem and you get stuck, you'll have it written down, but you could also go back and watch it as well. Okay, so one is on there. I'm not a big fan of like testing definitions, but you need to know what a derivative is. By the time you leave Calculus 1, you need to know what a derivative is. Now, I'm not sure, I might have picked something a little bit more on the answer key, but you will get full credit if you must state the derivative finds you slope at one point. Okay? You need to say something like the derivative, it finds slope or rate, if you want to use that word. You don't even write both, you just need slope at 1 point. That's the whole thing. You only need 1 point to find slope if you have a derivative. You want to say something like, it finds you the slope at 1 point. That's good enough for me. Like I said, I'm not a big definition fan, but when you hear the word derivatives, I don't want you crying. I want you to say, oh, I know. That finds me the slope at 1 point. All right. And then 2 is what's an integral. Okay, what I'm looking for there is, actually, should this be finds slope? Finds slope. When I say what's an integral, or maybe I should say what does it find, what I want you to say is it finds the area under a curve. Those will not be multiple choice. You are going to have to write those 2 out. They are on the test. Couple points each, because you need to say slope at 1 point. You need to say area under, from any graph. That they just use the word curve, but it's under any graph whatsoever. Just keep in mind it's to the x-axis. So like if the graph goes like this, I'm finding this area above. Let's just say this is A. And then it's finding this area here, B. Okay. On the test yesterday, it didn't go below. It kind of went, I think the graph went something like this. And people were trying to find the area here. And it didn't start until over here. So all the rectangles were above. But for some reason, some of you were drawing them below. And you were drawing a rectangle like this. That's the rectangle would go like this. Does that make sense? You have to go from the x-axis to the graph. Okay. So if for some reason, and that's okay, like if the rectangle went below, I just started the problem over here. But if for some reason it was in this area, then your rectangle is actually going below. But it's going from the x-axis. So the first 2 problems though on the test, you need to say slope at 1 point for 2 points, and then area under some type of any graph or any curve. All right. 3, I'm going to wait because I think it'll be easier to have the camera tomorrow. Like I'll be able to put that picture and draw on there. Okay. But remember, because the rest of the time we're going to do it algebraically. Remember, what is a limit finding you? I have to give you the x value. Okay. So a limit, I give you the x value, and you have to tell me the y value that the graph is approaching from both sides. What is the y value approaching from both sides? What's this y value? That's all you have to do. What's that y value? Okay. The rest of that, or a lot of them, when we go algebraically, there's going to be a hole here at 7. So it's harder to give the y value when there's a hole there algebraically, right? You can't just do the problem because the problem's going to say that there is no y value. Here, if a y value exists, that's your limit. That's no problem at all. But the problem is, how am I going to come up with this answer algebraically if my equation says that there's no y value? There is no y value. But the question for a limit is, what is it approaching? Can you tell me what that would be if the graph went through there? And so what we're doing in a lot of these 4, 5, 6, 7, and 8, we're filling in that hole. As soon as you fill in that hole, you've got this situation, and then algebraically, the equation will tell you what the y value is. All right, so let's take a look at 4. We'll come 3, we'll do tomorrow. So 4 says the limit, and this is the x value, instead of 7 on this problem, it is 3, as x approaches 3. What's the y value on this graph? Well, the problem is, if you just plugged in a 3 here, here, and here, you would get 0 over 0. So how am I algebraically going to come up with what this y value is if there's a hole there? So the question is, can we fill in the hole and then figure it out algebraically? All right, so when it's something like this, how do we fill in that hole? Look at that top. If nothing else, the top should be speaking to you to do what? Factor. Yeah, it's a beautiful trinomial. You got a little one underneath. You want to factor it. Slightly different, but almost similar to the one on the test. Now, yesterday we factored for a different reason, but kind of when you see that setup, we're going to factor. What multiplies to negative 15 but adds to be 2? X plus 5 and x minus 3. So in the limit, as x approaches 3, these cancel. I get the limit as x approaches 3 of x plus 5. This graph and this graph are the exact same, except here, when x was 3, there was a hole. And now here, when x is 3, we just filled it in. So we just went from this graph to this graph. So now I can figure out the y graph here by simply plugging the 3 in. So now it's 3 plus 5, so it is 8. I'm trying to think if there's anything else. Sometimes I write notes. What else? Okay, so what is this 8? That's the y value that this graph goes through, and this graph just is approaching from both sides. That's the y value that this graph's actually a line, that it goes through, but here, all we care about for a limit is what it's approaching. So here there's an open circle, but its limit is 8. Here it's a closed circle, but its limit is 8. Because this one is at least approaching 8 from both sides. Whether it's actually 8 at that value, we don't care. It's just what is it approaching. Okay, so the first one, these are going to be all on the test. The first one, you want to factor. Right? What do you want to do for 5? Kind of like you do the opposite of what they give you. So for 5, maybe I'll start over there. Did we get that one okay? For 5, you see that quantity. You see that 3 plus h squared. So for 5, limit is, they change it from x to h, but that's okay. of 3 plus h squared minus 9 all over h. That h of O is really representing that x value. I should say, it's the same thing as the x. I mean, if I was going to graph this, my x-axis would now be called my h-axis. All right, so what do we want to do with this, though? Same thing. I could plug in a 0, but I believe the 0 gives me 0 over 0. So that means there's a hole. We got to fill it in. To fill it in, you got to cross something out top and bottom. Can I just cancel these h's? No, this one's fine. This one's attached to a lot of stuff. It's attached to addition, subtraction, it's in a quantity. So we can't do that. So what do we want to do? There's only one thing you can do, right? Work on that square. Right? So the first one you're going to factor, this one, you're going to write it out twice and multiply. This is not 9 plus h squared. You cannot just bring that exponent in. It's close, but it's not the same thing. It is going to be 9, but it's going to be plus 3h, and then even plus h squared. And then you have this minus 9 tagging on. And then we still have the h on the bottom. All right, so now we can collect like terms. We've got 9 plus 3h, and 3h takes us to 6h plus h squared minus 9. And really, we can even collect what? Now that the parentheses are gone, it's okay to do this guy and this guy. And if you do it right away, that's okay too. Yeah, you don't have to do it in 2 steps. Those guys give us 0, so those guys are gone. All right, so let's go up here. The limit as h approaches 0. So I really now just have 6h plus h squared all over h. So these guys are gone. I just have these 3. Now we foiled, but what are we always going to come back to? We're going to factor, right? Take out an h out of the top. 6 plus, this just goes to h to the first over h. Good, yeah, that's h first. So these cancel. Limit as h approaches 0. Don't forget about that. I got it all the way down to 6 plus h. Beautiful. And so now I filled in that hole. Now I can evaluate. That's the y value that this graph actually has. This graph is approaching, but limit just says it has to approach. All right, so the first one you're going to factor, second one you're going to FOIL, but then you're going to end up factoring. What do we do for the third one in this category, but for number 6? This one was probably the trickiest to remember. The limit, stuck with h again. As h approaches 0, square root of 9 plus h minus 3 all over h. Same thing. When I go to see what the y value is, when x is 0 or when h is 0, I get 0 over 0. But a limit just says what is it approaching. It doesn't actually have to be a value there. But I got to somehow figure out that value. Okay? So that means I have to fill in the hole. To fill in the hole, you have to cancel. Anyone remember what we did with the radical? This is when you multiply top and bottom by the conjugate. When you've got that radical, and it doesn't matter where the radical is located. If it's on the bottom, you're going to do the exact same thing. You're going to find that radical, you're going to multiply by the square root of 9 plus h, that stays, and then it's plus 3 instead of minus. And you have to put that on the bottom as well. Looks like we just made a hot mess, but so when you see the radical, you want to think conjugate. Think conjugate, and that means that you change this sign. But you do have to put it top and bottom. You FOIL wherever the radical's at. So in this case, where it was originally. So we're going to, since the radical is in the numerator, we're going to FOIL this one. Don't FOIL this one. All right, so let's FOIL. What does this give you? Square root of 9 plus h times square root of 9 plus h gives you, right, just what's inside. Beautiful, 9 plus h. One of them. 2 underneath equals 1 outside. And then you can write this down if you want. This gives you a positive 3, and the radical just tags along. What does inner give you, though? Negative 3, and the radical just tags along. And then last gives you a negative 3 times positive 3 gives you negative 9. Remember, FOIL the one with the radical, just leave the other one. Plus. Okay, now that looked like a hot mess, right? What the heck did we do? But what's going to happen here right away? Those go away. A positive 3, maybe I should have went past that. Positive 3 and a negative 3, as long as the radicals are the same, that gives you 0. And what else? You can even do positive 9 and negative 9. Those go to 0. So after all that, we only have an h on top. And then we have that h on the bottom, which we're not going to multiply out, because what do we want to do? We usually want to factor and then cancel. So we've already got a factor, so now we're going to get. Okay. And what happens when we just when we canceled? We just filled in the hole. All right, so now we're doing the limit as h approaches 0. If nothing's on top, it is a 1. And then we got the square root of 9 plus h plus 3. I don't even need the parentheses because now there's no more multiplication. This graph and this graph are the same except where x or h was 0. That's the only difference. And now this is filled in, so now I can go evaluate it. 1 over square root of 9 plus 0 plus 3. So that's really just the square root of 9. 3 plus 3. That's the y value. So on this graph, 0, 1, 6 is a hole. But on this graph, 0, 1, 6, the graph's going right through it, so I can come up with my y value. All right, so the number 4, you're going to factor. 5, you're going to actually multiply that out. 6, conjugate. And then 7, you got to be able to add those fractions. You got to just simplify it. One thing is that we don't like a fraction in a fraction. So when you see all that, you got to think, okay, I just got to start simplifying it. Also be careful. I tried to fix it. That's a negative 4. Okay, so just be careful on those limits. Make sure you really, because it starts to get pretty small. Yeah. Okay. And then so 1/4 plus 1 over x over 4 plus x. To be honest, they really shouldn't give us this because basically they didn't simplify, right? We don't like fractions and fractions. And really we could try. You could plug a negative 4 in here. But I think it gives you 0 over 0, which tells you that you have a hole. All right, so how do we put this together? How do we do, since they didn't do it, we got to do the simplifying. You have to get a common denominator on the top. Between 4 and x, it's going to be 4x. You just need one of each. Okay. Kind of like if it was a 3 and a 5, you would say 15, right? Because you're really just pulling the 3 and the 5, putting it together. So don't let this x scare you. Just think of it as like a number 7, where I would need to just take those two and put them together. So here I multiply top and bottom by x. here, top and bottom, by 4. So now I have 1x, which is really just x, over 4x, plus, oh yeah, there should be a 4, right? You gotta match top and bottom. I don't know what it is. Yes, you have to match top and bottom because this gives it a value of 1. X over 4 is not a value of 1. That's not good. Okay, that's better. Okay, so now it's 4 over 4. And then if the denominators are the same, we can now add the numerator. But there's not really much I can do, but I can show that I want to do it. I'm going to do x plus 4, and then the nice thing is I only have to write the 4x once. And a lot of times, like when we're doing derivatives, we actually go the reverse. I think it's kind of good to see this. A lot of times we split it up. Once we get into derivatives, right, we like each one separate. So we would actually do the reverse. So this is kind of showing you both ways. This is when you get a common denominator, you only have to write it once. But it's okay to separate it if you need it. Both of these are okay depending on what you need. They come from each other. You can go back and forth at any time. And then don't forget we've got this guy. 4 plus x, I'll just do it in a different color. That's this one. If I want to make this a fraction, I can put it over 1. This guy is not okay. All this. Okay, so now we're in really good shape. Limit as x approaches -4. The top will stay. And then instead of dividing, multiply by the reciprocal. Now, for subtraction, we'd have to worry about because they're in a different order. You can still cancel them, but with subtraction, it's a little bit harder. But for addition, x plus 4 is the exact same thing as 4 plus x. Okay. So these will cancel. You don't even have to worry about like any negatives. We talked about that at the beginning of the year, but that was only when you're subtracting. For addition, doesn't matter. So those guys go away. All right. So what did when we canceled, what did we just do there? We filled in that hole. And so now we can algebraically find out what the y value was approaching. 4 times -4, 1 over -16. That's fine. If you put the negative on the top, that's fine, but you can just separate. So a very small y value, but that's okay. The only difference between this one and this one had a hole at -4, this one doesn't. Okay. But what basically we're kind of saying there is the limit is basically where's the hole at, because that's where the graph is approaching. All right. Okay, so we got, so 4 you got to factor, 5 you're going to multiply out, 6 you're going to do conjugate, 7 you just got to work with fractions, you got to get a common denominator. Okay, how about 8? Limit. I think I book weighted, and so that's why I did it later, but I really should almost do this first. This is a nice polynomial. We love polynomials. Yeah, they're continuous, there is no hole. If there is no hole, we should be able to come up with the y value right away. And so you can just plug it in. And that is your y value. And so if that's your actual y value, the graph has to be approaching that y value. There really isn't many other options. So that, yeah, what do we, 9 minus 15 plus 2, -4, -6 plus 2. I lost my good one. -4. Okay. Good. Yeah. And that's okay, can be negative positive, any of them can be, is it not, yeah. This should give us -6. And then, and negatives are fine, because that just means the y value is low, and that's okay. What else? So the question is, and maybe I answered it, but I didn't physically do it. How come I can't just take 3 and plug it into number 4? Yeah, you're right. It really doesn't even matter the top. You get a bottom of 0, but I think it's even 0 over 0. And that's why we have to do work. But yes, if you can take a number and get an answer, remember, when a 0 pops up on the bottom, that's no good, right? You don't get an answer out. That's the whole problem. So take advantage. If you can get an answer out, go for it, okay? If for some reason, and then we'll move on, but take a look at this. And you don't have to write this down, but take a look at, let me adjust for the limit x squared plus 2x minus 15 over x minus 3. If I wanted to limit when x was 10, I'm plugging it in and getting an answer. I mean, there's a lot of continuous parts on this graph. It's just at 3, there's the hole. So I can trick you. I'm not on the final, but keep in mind, if it's continuous around this value, you're plugging it in and getting an answer. So the only thing is, it's the harder ones, the ones you have to work for, and that's why they give it to you most of the time, is when there's that hole. Okay, when that bottom is 0. Okay, all right, let's take a look now at 9. 9? No, wait, is that right? Why did I label it 6? I'm officially crazy. This should have been labeled what? 8. Sorry about that. This was 8. All right. You okay with that? All right, let's take a look at 9. The limit as x approaches 3 from the plus side, which technically I could do that anywhere. I could do the plus anywhere, but usually when I do it, that means there's an issue. Okay, so kind of keep that in mind. And then x minus 5 over x minus 3. Okay, remember a limit, so when x is 3, whether there's a hole there or not, to be an official limit, it must be approaching from both sides. If it is not the same number on both sides, the limit doesn't exist. Okay, if it's not approaching the same number for both sides, and we'll cover that a little bit more when we go back and do 3. Okay, but if I put a plus sign here, then it only has to be, the plus means I only care about what's happening on the right side. And if my graph goes here, but it goes up here, and again, we'll cover that more when we do 3, that's okay. I only care about what's happening on the right side. Plus is right side. Let's see if this makes sense. Plus is right side, but you're heading left because you have to be heading towards that point. Negative means on the left side, but you're heading right because you have to head towards that point. But it is literally what's negative is what's happening on the left side, plus is what's happening on the right side. Okay, so when I plug a 3 in, I still get a 0 on the bottom, but I don't get a 0 on the top. How do I know that this is not a hole at 3? Because there's nothing to factor. I mean, this is pretty basic. There's absolutely nothing to factor. The hole comes from when I cross something out top and bottom. Okay. Now, if I could factor this, maybe there would be a hole there. But I mean, that's pretty straightforward. There's no, 3 is not an issue on the top. So if it only makes the bottom 0, does anyone remember what that is? If it only makes the bottom 0, you have an asymptote at 3. You have, if it only makes the bottom 0, There's no longer a hole, you have an asymptote. And these rational functions, the graph is either going like up here and down here, or it's going the blue. It would be going down here and up here. Maybe I should do it two separate. So this one's not going to be worth a ton of points, but there's a lot you got to think about in your head. So you have to realize that this is only making the bottom 0. I have to have an asymptote at 3. And so the graph is going up and down, or the graph is going down and then up. Okay. Now, if you have a graphing calculator and you want to graph this, you can do that. Go for it. And this is one place where I'm fine if you graph it. What is happening? I think it's this one. I think I graphed it. No, it's actually that one, isn't it? Good thing I checked. Okay, it's actually this one. Remember, what is the y value approaching from the right side of 3? What is the y value approaching as we're getting closer to 3? It's headed down, the y value. It's headed down to negative infinity. Okay. Is it ever going to reach 3? No. But we don't care what's happening. We only care what is approaching. Okay. As we get closer and closer to 3, the y value is going to get lower and lower and lower. This one, there's nothing you can do algebraically because there's an asymptote. The graph is never going to be at 3. For a hole, you can fill it in, kind of fake it or get a similar graph. You cannot do that for an asymptote. You will never hit, there's no way to fill in an asymptote. But does anyone remember how we did do it algebraically? Graphing is probably the best for that. The way we did it algebraically is we just chose a number on the right side of 3. So 3.1. And then we simply plugged it in. 3.1 minus 5 over 3.1 minus 3. And then all we did was we said, okay, this is a negative over a positive. So it's negative. The y values are negative. But on your own, you have to know that you're an asymptote, you're at an asymptote, and the answer has to be positive infinity or negative infinity. And then when it worked out to negative, I knew the y values were negative, so it would be negative infinity. So if you don't have a graphing calculator, you have to realize that 3 only makes the bottom 0. There's no way to cancel anything out. I must be at an asymptote. If you're at an asymptote, you can pick numbers around it, but automatically 50-50 chance your answer is either positive infinity or negative infinity. If you know you're at an asymptote, it's got to be one of those. Okay? And so, but you have to know all that on your own. And then what we did is you could either graph it and visually see it, or we chose a number. Now, if this was approaching 3 from the negative side, what number would we use? Maybe something like, what would be to the left of 3? 2.9. Yeah, 2.9. Now, 2.9 minus 5 gives me negative. But what does 2.9 minus 3 give me? A negative as well. This isn't on there, but it's a big. So that's positive. But then I have to know on my own, I'm at an asymptote. So it either has to be positive or negative. Okay, but that was with the negative. Okay, this one goes with the answer. But just thought maybe you'd go again. But there's a lot there that you have to remember. Now, it's not 100%, but for the test, I'm going to put that little plus or minus. which is a really good indication that there is something happening different on either side. It doesn't have to be, but a lot of times that's what they do. All right, so a lot to remember on those limits. And then you still got to do the algebra. Okay, we'll come back one more time to 3 tomorrow when I can put it under the overhead. The camera, I guess you call it. Okay. So you do not have to do derivatives with limits. I'm not going to have to put that on the final. My thing is, do you remember all the shortcuts? So for 10, 4x to the third minus x squared plus 3x minus 5. All right. Can you find the derivative? So we're back to derivatives. The most basic, the power rule. Roll it down, subtract 1. Beautiful. Yep, that's it. And when you roll it down, you multiply. So 4 times 3. 12. Can I just write 12? Are we okay? I think we're pretty good. Roll it down. Remember, just multiply. Roll it down. If there's nothing there, you're multiplying technically by 1. Make sure that I subtract. Roll it down. And then subtract 1. So now that's x to the 0. So that's gone. And -5 goes away, because remember, -5, technically, you could think of it as x to the 0. When you roll it down, technically, you could subtract 1, but the 0 overrides everything, and so it's gone. And so that's our derivative. We could write it like this if we kind of want to correlate it. Don't forget, we could also write it as dy dx. So that, because we were using that in chapter 4, so it might just be good to see, like, oh yeah, I could write it like this. All right, how about 11? I'm hoping 10's easy, but 10 will be on the test. So you're like, okay, I'm gonna go to 10 right away, get some points. Let me find it. All right, remember f of x, same thing as y. We're better. What do we have to do for 12? We just have to take the time to rewrite it. Okay. Now, this first term actually is the way we prefer it, but when we're doing derivatives, that x has to come to the top. This is much better, 7x to the -4. And then this is, how are we doing on cube roots? 1/3. Square roots are 1/2, cube roots are 1/3. The exponent on x is a 1, that's why it's not written, and then the radical goes on the bottom. Okay, and then we're writing, this is still f of x. And then we can actually take the derivative, roll it down, subtract 1. So just be careful here with that negative. When you subtract 1, where's my red? When you subtract 1, it goes to -5. So roll it down. 7 times the -4, -28, and then subtract 1 actually takes you to -5. Right? Roll it down, and if this is the one that you have to write, 12/1 times 1/3. That's okay. Roll it down, and then subtract 1. 1/3 minus 1 should take you to -. I mean, you could we probably should clean this up. So -28. I don't care if you push the x back to the bottom or you leave it. This one gives us a nice 4. This one's actually negative as well. But you can leave it. I don't know what I did. It's weird. I moved this one positive, but then I left that one negative for some reason. I don't even know if I should say it. Don't put a +c when you're taking a derivative. Okay, so now I let derivatives find you slope. But I have this equation here. Where's the slope? Remember, if I'm doing it on a curve, the slope's always different. So you have to say, hey, I want the slope when x is 7. Okay, then I can take a 7 and plug it in there and get a numerical answer, which would be the slope or the rate. Okay, it's always changing. So, hey, I want the slope when x is 1. Okay, now I know that. Now I can put a 1 in and come up with the slope. Okay? And remember, this curve, whatever it is, we're actually finding the slope on this equation, this graph. I want the slope on this graph when x is 1. Okay, I go down and use it down there. Okay? So those equations find you the slope. And it's always different at every point, or could be. So we're waiting, we're in holding pattern until you tell us where you want the slope. All right, good. We did that, we did that. Let's do 12. Quite as far as I thought. And it might. Let's see. If we can get through 12 and 13, fine, and if not, that's okay. Okay, now we step it up a notch. What do we have to do for 12?
Product rule.
Beautiful. Product rule is exactly right. 5x squared times sine of x. And there really isn't any notation. I mean, even the 5 times x squared. But if it is a constant, then you don't need the product rule. Okay? I could show you why. If we have time, maybe I can even do it on Monday, depending on how much time I have. But the constant, you don't need the product rule. But otherwise, we're going to group this together. Even though this is multiplication, we can group this together. And then there's your times. Okay, so remember, it's generic. This f of x is talking about the function. But now this f of x is just simply talking about the first factor, the first thing you're multiplying. So this is going to be 5x squared. Its derivative is, well, it does subtract 1, so its derivative is 10x. Good. And then the second thing we're multiplying, the second factor, is sine of x. Now, its derivative, the derivative of sine is cosine. Don't do any exponent stuff. Remember, the exponent is gone. When you do trig, you just have to remember the derivative of sine is cosine. And then I think I'll look to, oh yeah, I'll make a note. I had to look. I think I give you this on the test. First times the derivative of the second plus the second times the derivative of the first. And then it's just a matter of plugging it in. First times just take your time times the derivative of the second plus the second times the derivative of the first. That answer is okay. You really probably should have these parentheses. The better answer, so you wouldn't need the parentheses, is to put the 10x first. But as long as you have those parentheses, then you're okay. If not, you just have to be a little careful, because is it sine of these three things? You know, this has nothing to do with the sine. You just take it times at the end. But then we could probably factor something out, but it doesn't. For me, that's fine. I'm still going to have the same amount of like stuff, so it doesn't really matter. If you get that far, you're good. All right, let's do 13. We'll end on 13. That'll be perfect. We'll end on 13. What do we have to do for 13? Oh, yeah, you're right. I have to say product. Yes, quotient rule, right? And done giveaway, right? You got that division? Yeah, very good. Quotient rule. I think I say that a lot. All right, so we got x squared plus x minus 2 over x to the third plus 6. So yeah, quotient rule. Just take your time. It just ends up being a little bit longer, but it starts out, and kind of I wanted to finish it because it starts out the same. So f of x is your numerator, x squared plus x minus 2. Its derivative, perfect, 2x, yeah, a lot of people have trouble with x. I'm glad it popped up somewhere. Maybe this is not the best place for it, but 2x plus 1. The derivative of x goes to 1, derivative negative 2 goes. And then g of x is your denominator. And then its derivative, perfect, roll it down, subtract 1. And then, and I'll give you this pattern. Remember, g's on the corner, each one's different. So second times the derivative of the first minus first times the derivative of the second. And then on the bottom, but then you have to square. And these are always different. So if I know it's g, I know f is coming next, and these are always different. So if g was regular, it has to be the derivative. Then I know this one's a derivative, so that one has to be regular. And then there we go. Okay, so then it's just a matter of plugging it in. X to the third plus 6. And then the derivative is 2x plus 1. Just be careful here, minus, and then you need a bracket because first you have to multiply. X squared plus x minus 2. And then the derivative, that wasn't too bad, 3x squared. First, you have to multiply and then distribute that negative. And then all over x plus 3 to the 6 squared. We pretty much never do anything with the bottom. So just make sure you square it and then leave it. All right, so now here, this we have to FOIL. So we get 2x to the fourth. When you're multiplying, you add exponents. X to the third. Inner gives you 12x, and then last gives you 6. Nothing, we don't collect like terms at all there. I mean, there's none to collect. Here, the minus, okay, first I have to multiply. At least I don't have to FOIL, but I do have to distribute. Add those exponents, 3x to the fourth, 3x to the third, and then minus 6x. Multiply, then distribute. 2x to the fourth, so I'm just going to rewrite this. Oh, I know, one thing we could do is, as I'm distributing, I could line it up, negative 3x to the fourth. And that's just something I've kind of been doing of late. Sometimes it gets too long, but usually that's what I do. Minus 3x to the third. And then that would actually be plus, plus 6x squared. But do we see that it's plus? All right, so then not a lot goes together here. So I think the final answer is pretty long. Was it originally a G, I think it was? Okay, so this would give me negative x to the fourth. This would give me negative 2x to the third plus 6x squared plus 12x plus 6. And then don't forget, I kind of left it. Don't forget the bottom. Was that right or no? Yeah, it was that long. Okay. Sometimes they condense down really nice. And then don't forget your denominator when you're trying to collect all those like terms in the numerator. Okay, and what that would find, I would have to use that whole equation to find slope. You just got to give me the x, and then I got to take the time to plug it in. All right, good. Okay, so we got through 13. All right, so we'll just keep cruising. If you want to work ahead, and then, or if you just want to review these, you can. It's kind of up to you. I think we're on route. I think we'll be able to get to most of these between Friday and Monday. We do have to go back and do 3 of them. But, okay, so let me pause this. Okay, you guys were good. You guys didn't holler. Are you guys okay out there in TV land? Okay. Well, hopefully I'll see you Friday. Okay, how are we here?